Hello everyone. This is part 2 of our review for the final exam, and we pick up where we left off with some laws of exponents now. Remember, first law to consider is the product rule for exponents. If we multiply bases, we keep the base and we add the exponents. So in general, x to the m times x to the n is x to the m plus n. So in the first question, what we could do, you don't need to do this, but if you wanted to, you could group the coefficients together. So the -5 and the 3, and then group the powers of x together, x to the third and x to the fourth, and then just multiply the coefficients. So -5 times 3 is -15, and multiplying the common bases, we keep the base of x, and we add the exponents. 3 plus 4 is 7. So this middle step's optional. Next property, in part B here, we use the power of a product rule, which says if you have, let's say, x times y to the nth power, so a product raised to a power, you raise each factor to that power, so x to the nth and y to the nth, and keep it as a product. So an intermediate step here would be, and this is extended to more than 2 terms, if you wanted to show this literally, every factor gets raised to that power. So -6 gets squared, the a cubed gets squared, the b to the 5th gets squared, and the c gets squared. And it's understood that's c to the 1st. If you want to slide the 1 in there, that's fine. Now at that point, to evaluate the coefficient, -6 squared is -6 times -6, which gives us positive 36. And then the rule we're using here is the power rule. If we have x to the nth raised to the nth, so if we take a power and raise it to a power, we keep the base and we multiply the exponents. So x to the m times n. And so a cubed raised to the 2nd power, keep the base of a, multiply the exponents, we get 6. Similarly, b to the 5 times 2 is 10, and c to the 1 times 2 is 2. So again, the intermediate step's not necessary. If you want to go right to the answer, that's fine. And then part C uses the properties we've already talked about, as well as the power of a quotient rule. If you take a quotient, raise it to a power, so let's say x over y is a quantity to the nth, we raise the numerator to that power, so x to the nth, and we raise the denominator to that power, so y to the nth, and we keep it as a fraction. So combining the quotient, power of a quotient, power of a product rule, basically everything that's in parentheses gets raised to this power. And so if you want to show that literally, you'd have -2 that gets cubed. This is u to the 1st. If you want to slide the 1 in there, gets cubed. Similarly, v to the 1st gets cubed, and the w to the 6th gets cubed. And then evaluating each of those, -2 cubed is -8. U to the 1st cubed, we're raising a power to a power, so keep the base and multiply the exponents, so that's u to the 3rd. Similarly, v to the 3rd, and w to the 18th. So there's some laws of exponents. Next to scientific notation, I included both situations that you can encounter. You're only going to get one of each of these on the exam, but it could be such that the number is bigger than 1 or maybe less than 1. But remember, the scientific notation, the idea is to write the number such that there's only one non-zero digit before the decimal point. So I would write this as 3.14, and then it's always going to be times 10 raised to some power, and the power is determined by how many places we move the decimal point to get to the position where the arrow is. So in this case, you could use little loops, the decimal points on the end here, following the last 0, and you can count 1, 2, 3, 4, 5, 6, 7. And because the number is bigger than 1, the exponent's going to be positive. And so if the number is less than 1, the exponent's going to be negative. Now, let me recopy this. Actually, I'll write it as point, so I could show my loops a little bit better. Let's see, there's 1, 2, 3, 4 zeros, and then 2, 7, 1 after the decimal. Alright, so we know it's going to look like this for sure. One non-zero digit before the decimal would make it 2.71, and then it's always times 10 to some power. Count the decimal places, 1, 2, 3, 4, and 5. But because the number was less than 1, the exponent is a negative 5. Okay, and then if we go in the opposite direction, if we want to write it in standard form, then you write down the number and move the decimal point how many ever places the exponent says, so 5 in this case. And if the exponent is positive, that means the number is larger than 1, so we're going to move the decimal to the right. So 1, 2, 3, 4, and 5. Now these little loops are helpful because they help you to realize how many placeholders you need. And the placeholders are the zeros. So then this would be 716,000. And if you wanted to, from the right, every 3 digits is a period. So 716,000 if you like. Now this one has a negative exponent on the base of 10. So that means the number is smaller than 1. And so therefore the decimal is going to be moved to the left 7 places. So I'm going to start over here a little bit to the right, so I can move the decimal point 7 places to the left. So counting using our little loops again, 1, 2, 3, 4, 5, 6, 7. So there's the new decimal. Fill in all the zeros. Looks like there's 6 of them. So this would be, I always put a 0 out in front of the decimal. Not necessary, but conventionally good practice. And then we had 6 zeros and the 1, 4, 3, 2. Okay, next idea, combining like terms. And remember that like terms have the same variable and the same exponent. So you could group the like terms together. For example, I could write the 5p squared and just move the 4p squared over with it, and then group the constant terms together. Or without that step, you could just simply, I like to do the underlining method. 5p squared plus 4p squared would give us 9p squared. And then positive 3 combined with the negative 7 would give a negative 4. So you can see that's the same thing obtained if you do the little grouping method. So either way, whatever you're more comfortable with. Here are some questions of adding and subtracting polynomials. And so the thing about adding or subtracting polynomials, actually, let me recopy these. And what I'm going to do is, in front of the second polynomial, there's a plus and there's nothing written in front of it. So consider that to be a 1. And in fact, also consider that in front of the first set of parentheses is really a 1 also, if it's not written. And adding polynomials, basically you just remove the parentheses by the distributive property. But it's really easy because 1 times anything is itself. So we get minus 6y squared minus 4y, and then this plus 1 distributed. That doesn't change anything either. That is, we just have plus 2y squared plus y minus 4, and then we can combine like terms. So I'm going to use the underlining method for the squared terms. There's negative 6y squared combined with the positive 2y squared gives us negative 4y squared. Then there's the y terms, or the linear terms, a negative 4y and a positive, that's understood to be a 1. Y combined to give minus 3y. And then it looks like the only constant term is the negative 4. So we just have to tag that along. And when we get to subtraction, pretty much the same idea, but I'm going to choose to rewrite this and include the 1's in front. So in 1 in front of the set of parentheses, x squared plus 5x plus 4. But now this is very important here. This minus behaves as a negative 1 that needs to be distributed to the 3x squared minus 8x plus 7. So the difference is between letter A and letter B, when we distributed with addition, nothing really changed. Basically the parentheses just dropped and all the signs remained the same of each of those terms. But when we're subtracting, the first term upon distributing the 1, nothing changes there. That is, in this case, we get x squared plus 5x plus 4. So it's like the parentheses were just dropped. But when we distribute the negative 1, then the signs of each of these terms change. So negative 1 times 3x squared is minus 3x squared. A minus 1 distributed to the minus 8x gives positive 8x. And the minus 1 distributed to the negative 7, or excuse me, distributed to the positive 7 gives us negative 7. And now we can combine like terms. So notice how the polynomial that we had subtracted, all of the signs changed. The 3x squared became a negative, the negative 8x became positive, and the positive 7 became negative. And now we just combine the like terms. There's an x squared if you want to put a 1 in front of it. That's fine. Combined with the negative 3x squared gives negative 2x squared. Maybe I'll underline the x's twice. There's a positive 5x combined with a positive 8x to give us positive 13x. And then I think I'll circle the constant terms. And remember, it's the sign that precedes the term that belongs to that term. So we're combining a positive 4 and a negative 7 to get negative 3. Okay, so next page. We've got 2 pages left. Next page is more work with polynomials. Here we're going to multiply the polynomials. So here we have a monomial times a polynomial. So I'm going to choose to rewrite it what happens when we have a monomial multiplied by a polynomial is just the distributive property. So we're taking the negative 4a squared and we're distributing it to each of these terms. So here we should be proficient enough to know that we just multiply the coefficients. So a negative 4 times 5 is negative 20. And then when we multiply the common bases, a squared times a squared, we keep the base and we add the exponents. So a to the fourth, distributing the negative 4a squared to the next term. Negative 4 times negative 4 is positive 16. And then we have a squared times a, that's a to the first, it's understood. And multiplying common bases, again, we keep the base, a, we add the exponents, 2 plus 1 is 3. And then finally distributing that negative 4a squared to the 5, we get negative 20, and the a squared just tags along. So next situation is a binomial times a binomial. And we should recognize that we need to FOIL. So show it literally here. I'll set it up. Go through the FOIL process. 3x times x is the product of the first. To give, I'll leave some space here for my other arrows, but that gives us 3x squared, because that's x to the first, we add the exponents, we get x squared. The outer terms are 3x times 1, or just 3x. Make sure we put a plus in there to separate the terms. The inner terms, minus 8 times x, minus 8x. And then finally the last terms, minus 8 times positive 1 is minus 8. And then, as we've seen many times, after foiling, the outers and inners can be combined. So the first term, 3x squared, recopied, and combining the 3x positive and the 8x negative, we get negative 5x, and then we just need to recopy that constant term of negative 8. Okay, and then we get to some factoring regarding polynomials. Remember, the first thing you look for is the greatest common factor. And just compare factor by factor, compare the coefficients between 14, 4, and 16. Just a 2 is in common. And then compare the powers of x. We have x to the fifth, x squared. This is x to the first. Remember, the greatest common factor is the least power. So x to the first, or just x. And then upon factorization, the easiest way is to reverse the distributive property. That is, write down the greatest common factor and think of the fact that we're taking 2x times something to give us this first term, 14x to the fifth. So 2 times 7 gives us 14, and I have one factor of x, I need 5, so I'm missing 4 of them, I need 4 more. Distributing, again, we're reverse distributing. You can think about this as division, as I've talked many times. You could have thought of this as 14x to the fifth divided by 2x. 14 divided by 2 is 7, and 4x to the fifth divided by x to the first is x to the fourth. But I'd like to think about it as reverse multiplication again. So continuing, 2x times what gives negative 4x squared. I'd need a negative 2 to get negative 4, and I'm missing one factor of x. And then the 2x times what gives 16x, and all we need is a positive 8 there. And then you close the parentheses, and let me just recopy this without the arrows cluttering everything, and that would be our answer. Okay, then we get to factoring trinomials, and actually C is special. But factoring trinomials, remember, they come from the product of two binomials. And you're only going to see on the final exam the special case where the leading coefficient, or the coefficient of the x squared term, is equal to 1. And if it is, then in the product of the two binomials, the first term of each is just going to be x. And then to determine the second term of each, we list the factors of the constant term. In this case, negative 45. So that would be 1, negative 45, negative 1, 45. See, 3 and negative 15, negative 3 and 15. And then the only other pair of factors are 5, negative 9, and negative 5, and positive 9. And we're looking for the pair that combines to give us the coefficient of the middle term, so negative 4. And it looks like, let me just make this look a little better. That was a negative 5. And it looks like the pair that combines to give negative 4 would be a positive 5 and a negative 9. So x plus 5, x minus 9. And you could check this, remember, by calculating. You can literally FOIL, or if you trust that you forced the first and the last products correctly, you could check by just calculating the product of the inners, positive 5x, product of the outers, negative 9x, and make sure that they combine to give you the coefficient of the middle term. So the correct answer, yes, that checks. X plus 5, x minus 9. So you get a couple of these. Here's another example, which again, we should recognize as a quadratic trinomial. Factored in the product of two binomials, first term of each binomial is x. To determine what the second terms are, list the factors of 35. Now that's a positive 35, but note how the coefficient of the middle term is negative. So the positive factors actually aren't going to be the ones we're looking for. But let's list them all anyway. We've got 1, 35, negative 1, negative 35. And I think the only other pair of factors is 5 and 7. Or negative 5, negative 7. And the pair that combines to give us the negative 12 would be the negative 5 and the negative 7. So x minus 5 and x minus 7. And you could double check that if you like. Now this you have to recognize as the difference between two perfect squares. And when we have that of the form a squared minus b squared, it's factorable into the product of a minus b and a plus b, or vice versa. So look for these. They occur quite often, and you can recognize them easily because, to begin with, there's not 3 terms like the previous examples. There's only 2, and it's quadratic because it's a squared term. And just look for the difference and the perfect squares. And so we know x and x for 16, 4 and a 4, and just make one of them negative and one of them positive. It doesn't matter which way, if it's x minus 4, x plus 4, or x plus 4, x minus 4, either one is acceptable because multiplication is commutative. Alright, so then we get to equations, and standard form for a quadratic equation is everything to one side set to 0, so ax squared plus bx plus c equaling 0. And if it's of that form, then we factor. So this is already set up. Has to be set to 0, so it is. So we're going to factor that quadratic trinomial as normal. X and x, make sure you write equals 0. Okay, if you want to use the factor method, that's great. We're looking for factors of positive 16. So 1 and 16, negative 1, negative 16, 2 and 8, negative 2, negative 8, and 4 and 4, negative 4, negative 4, and that would be it. And now we're looking for the pair that combines to give negative 10x, or negative 10. That'd be the negative 2 and the negative 8. So this factors is x minus 2 as a binomial times the binomial quantity x minus 8. And then there's a little bit more work to do. Recall that once it's factored, we use what we call the zero factor property to set each factor equal to 0. So x minus 2 equals 0, x minus 8 equals 0. Typically we'll draw that line down the middle. And then what we have is two linear equations that we solve separately. Here we're going to add 2 to both sides. You don't really need to show that. You could do that mentally. Get x is 2, and similarly here, add 8 to both sides. Get x is 8. And so the solution is that there's two solutions, 2 and 8. Typically my math lab tells you to list the solutions and just separate them by a comma. Now that's standard form again, everything to one side set to 0. And it's quadratic because we know it's a squared. This is quadratic, it's squared. And everything's to one side, it's in standard form. But there's not 3 terms, there's only 2. So don't forget that the first thing you ever look for upon factoring is the greatest common factor. And in this case it's x to the first, or just simply x. So if I factor out, I'm going to be left with a binomial, only 2 terms. Because when we factor a greatest common factor, there's as many terms in parentheses as there is in the original expression. And then if you reverse the distributive property, you could say x times what is x squared, that would be an x. And then x times what is negative 3x, and that would be a negative 3. And so, okay, if I get rid of the clutter of the arrows, that's what we have upon factorization. And now we set each factor to 0. So x is 0, that's actually a solution, and x minus 3 is 0. And so we have adding 3 to both sides, we get x equals 3. So the two solutions, 0 is a solution, so x equals 0 and 3. Okay, here's one more quadratic equation. And this one is not in the standard form. Because remember, once again, the standard form is everything to one side set to 0. So ax squared plus bx plus c equaling 0. And you could show literally subtracting 27 from both sides. But I'm just going to use this little method of indicating a mental transposition of the 27. So that we get x squared minus 6x. And when we transpose, remember when we move a term from one side of the equation to the other, becomes its opposite. So that'd be minus 27 would equal 0. And now that we have it, well, let me just show you what it would look like if you showed it literally. You'd subtract 27, subtract 27. Okay, on the right we get 0, that's for sure. See, but on the left it looks a little strange, but you have to realize that you can't combine anything. There's an x squared, there's an x, and the negative 27 is a constant. so nothing can be combined, and you just get the standard quadratic trinomial equation in standard form. So no matter how you got there at that point, do the factorization. Again, I'm making it easy so that the leading coefficient is 1, so that in the factorization, just an x and an x. And moreover, we could use the factoring method, where we list the factors of the constant term, in this case the negative 27. So 1 negative 27, negative 127. Let's see, I think the only other pair of factors are 3 and 9, right? So 3 and negative 9, negative 3 positive 9. And then we're looking for the pair that combine to give us a negative 6. And that looks like the 3 and the negative 9. So x plus 3, x minus 9. Then by the zero factor property, set each one to 0. So x plus 3 is 0 and x minus 9 is 0. And then to solve for x, if you need to show it here, these are both linear equations now. So here we would subtract 3 from both sides. So x is negative 3. Here we would add 9 to both sides. So x is positive 9. And again, as a solution in my math lab, negative 3, 9 separated by a comma. Okay, and next pair of questions are simplifying rational expressions. And remember, it's really just, instead of one factoring problem, we have two factoring problems. And in the first example, remember the first thing we have to look for when factoring excuse me, is the greatest common factor. And in the numerator between 6 and 30, 6 is common. So if I factor out the 6, again I'm going to use the method of reversing the distributive property. 6 times what gives 6x? That would be an x. And then 6 times what gives negative 30? We'd need negative 5. And then from the denominator, the greatest common factor there is a 5. And then again I'll reverse the distributive. 5 times what gives 5x? That's x. And 5 times what gives negative 25? That would be negative 5. Okay, I'm just going to recopy this. I'll get out the clutter of the arrows. So 6 times the binomial x minus 5 over 5 times that same binomial. And now we can cancel the x minus 5s. Because remember, you can't cancel the sum or difference, only a product. That's why we factor, to make them products so that we can cancel. And then it looks like we just have 6 times 1 or 6 over 5 times 1 or 5. Okay, and then for part B, there are two factoring problems essentially again. Both factor as the product of two binomials. So in the numerator, an x and an x. Okay, we're looking for factors of positive 32. So 132, negative 1, negative 32, 216, negative 2, negative 16. Let's see, 4 actually does work, right? 4 and negative 8. Negative 4 and 8. Or I'm sorry, 4 and positive 8, because the product's positive. Factors of positive 32, so 4 and 8, negative 4, negative 8. And I think that's it, right? And so the pair that combines to give us the positive 12 is the positive 4 and positive 8. So x plus 4, x plus 8. And then for the denominator, same idea. X and x. Now we're looking for factors of negative 24 that combine to give us a negative 2. So 1 and negative 24, negative 1, 24, 2 and negative 12, negative 2, 12. See, 3 and negative 8, negative 3, 8. 4 and negative 6, negative 4, 6, and I think finally that's it. And the pair that combines to give us the negative 2 is the positive 4 and the negative 6. And then you can see that the x plus 4s are now common. So we can cancel those out, replace them by 1s, and we just have the binomial in the numerator of x plus 8 over the binomial in the denominator of x minus 6. Okay, then the last set of questions have to do with radicals, and remember we have a couple rules for radicals. Radicals are really powers, and here we have the square root of a product property. Square root of a product is the product of their square roots. So square root of a times square root of, square root of AB is the square root of A times the square root of B. So in the first example, we could break this up to be the square root of the coefficient 36 times the square root of the variable x to the 4th, and then the square root of 36 is 6. And remember, with variables, if the power is even, then we just divide the exponent by 2 and remove the radical. So the square root of x to the 4th is x squared. And remember, theoretically, that's because if you take x squared and square it, you get x to the 4th. But make sure you, at the same time you divide by 2, that you remove that radical symbol. Now, if the number is not a perfect square, then the method was to factor out, write it as the product of two radicals, where the first of which contains a perfect square that is a factor of that number, of the original radicand. And if you work your way up the list, if you were to list all the perfect squares, like 2 squared is 4, 4 squared is 16, 25, 36, 5 squared is 25, 6 squared 36, and so on. You can work your way up the list, and the first one that divides evenly into 75 is 25. And 25 times 7 is 175. And then you could literally take the square root of 25, and that will come out of the radical, because the square root of 25 is just the number 5. So 5 comes out of the radical, and you have to carry along the square root of 7. Okay, so then we get to this example, which initially you could start as the square root of 49 and the square root of, well, actually, here's a better idea. Break it up into two radicals. And the reason why I need 2 is because, well, there's 2 factors, but 8 to the 19th is not a perfect square because it's an odd numbered exponent. 49, I know, is a perfect square because 7 times 7 is 49. So what we do recall is we take out as many factors as possible from the variable, which is always going to be one less, in this case a to the 18th. And then the leftovers would just be a to the first, because a to the 18th times a to the first is a to the 19th. And then you could take the square root of 49, which is 7, and the square root of a to the 18th, again, we're going to divide the exponent by 2 and remove the radical, so it becomes a to the 9th. And then that square root of a to the first just has to actually stay as part of the product. Okay, and then the final example. This uses the property that the square root of a over b is the square root of a divided by the square root of b. So we'd have the square root of 80 over the square root of m to the fourth. Now the square root of m to the fourth, that's an even exponent, so that comes out as m squared. But the square root of 80 actually can be broken down into the product of two radicals, the first of which is a perfect square that's a factor. And again, if you work your way up the list here, the first one you're going to find that divides evenly into 80 is 16. So we put the 16 under the first radical, and the leftovers, 16 times what is 80, that's 5, goes under the second radical. And then we just take the square root of 16, which comes out of the radical as 4, tag along the square root of 5, and we get the m squared in the denominator. Alright, so that's it. That's what the test is going to be like. And I wish you all the best of luck, not only on our final exam, but in all of your future academic endeavors.